As World War II comes to an end, scientists discover the secret of the atom, unleashing death and destruction on an unimaginable scale. Now they are racing to discover the secret of life. It will be the find of the century. It's May 1st, 1952, and what these scientists gathered at the Royal Society don't know is at this very moment, close by in a London lab, an X-ray camera is clicking off a 100-hour exposure of something called DNA. When developed, this photograph will reveal the structure of DNA and the key to understanding how the blueprint for all life on Earth is passed down from generation to generation. Two of the most determined of the DNA detectives are Francis Crick and an American, James Watson. Also at the Royal Society is a 31-year-old British scientist named Rosalind Franklin. She is responsible for the crucial X-ray photo. As Watson, Crick, and their colleague Maurice Wilkins strive to solve the puzzle of DNA, Franklin's work will pave the way. Without her knowledge, they will gain access to her findings and her remarkable X-ray image of DNA. It will lead to one of the greatest discoveries in science, and some believe, to one of its greatest injustices. Up next on Nova, Rosalind Franklin and the secret of Photo 51.
Corporate funding for NOVA is provided by Sprint and Microsoft. Additional funding is provided by the Park Foundation, dedicated to education and quality television. And by the Corporation for Public Broadcasting, and by contributions to your PBS station from viewers like you. Thank you.
In 1962, a Nobel Prize is awarded to James Watson, Francis Crick, and Maurice Wilkins for their groundbreaking work on DNA. It is one of the greatest achievements in the history of science, often described as the key to unlocking the secret of life. A few years later, James Watson publishes his personal account of the discovery. In The Double Helix, this slim, best-selling book, he depicts a race to determine the structure of DNA and introduces a little-known scientist named Rosalind Franklin.
I don't think anybody would have heard of Rosalind Franklin. I certainly wouldn't have written the book unless James Watson in 1968 had written The Double Helix. But in it, there's this character, the terrible Rosie, this bad-tempered, blues-stalking who hoarded her data, who wouldn't let the men see it, you know, and lashed out at all of them. They were all terrified of her. And it really makes the whole story go.
Watson's casting of Franklin as villain works as a literary device. But who she is in his book and who she was in real life are quite different. And, unfortunately, Franklin wasn't around to defend herself. She died at the age of 37, a decade before The Double Helix was published and became a bestseller.
When The Double Helix was in rough draft, Harvard University Press, which was planning to publish it, asked that all those so candidly mentioned be given a chance to read it. And they did, and Wilkins and Crick above all, but not only, objected most strongly.
As Francis Crick wrote to Watson, "Your book is misleading and in bad taste. It does not illuminate the process of scientific discovery. It distorts it." Maurice Wilkins complained that the book was unfair to almost everyone mentioned, except Professor Watson himself. And referring to Rosalind Franklin, he asked Watson, "Is there any mention in your book that she died?"
Oh, well, that was what the main thing in the objecting to the Jim's book was, his portrayal of Rosalind. There was all this silly natter about the wrong clothing or something. I thought this is pretty inane and not true. I mean, she was, to say the least, a very presentable person.
Who was the real Rosalind Franklin? And what is her contribution to one of the greatest breakthroughs in science? Rosalind Franklin was born in London in 1920 into a family that achieved wealth through banking and publishing. They had a proud tradition of scholarship, philanthropy, and involvement in social causes.
The Franklin family was one of a very select group of English Jews who came to England during the 18th century. They became very wealthy, a very close network, very English in their manner, more English than the English.
From an early age, Rosalind stands out. She enjoys memory games, and an aunt writes, "Rosalind is alarmingly clever. She spends all her time doing arithmetic for pleasure, and invariably gets her sums right." Her parents send her to St. Paul's Girls' School, which, despite its name, had no church affiliation. What it did have was a strong tradition of preparing girls for a career. Sue Richley and Ann Piper attended St. Paul's and were Rosalind Franklin's lifelong friends.
She was the best at science, she was the best at maths, and she was just one of the best in that year. The best, I would say, in that year. She played in the teams.
Tennis, hockey, lacrosse,
Yes.
netball, cricket.
She combined using her mind play with having a certain natural ability.
She always expected that if she undertook something, she would be running it.
Yes.
She would wish to be, expected to be like that.
Yes.
While Rosalind excels academically, the outside world is encroaching. The Nazis are on the march. As Jewish refugees flee the Nazi onslaught, the Franklins are active in finding safe haven in England for those who manage to escape. Rosalind is anxious to do something useful with her life. She finishes a year early at St. Paul's and wins a scholarship to study physics and chemistry at Cambridge University.
In 1938, Rosalind arrives here at Newnham College, one of the women's colleges of Cambridge University. In her classes, she's introduced to the new subject of X-ray crystallography.
This technique can reveal the hidden atomic structure of matter in its crystalline form. Atoms are too small to see under light microscopes, so crystallographers shoot invisible X-rays at them, which then bounce off or diffract onto a detector such as film. By applying math to the diffraction pattern, it's possible to calculate the three-dimensional form of even the most complex molecules.
In her X-ray diffraction work, Rosalind joins the small band of the human race for whom tiny specks of matter are as real as billiard balls.
In 1939, as Franklin steps into the world of science, Cambridge University appoints its first female professor, and Britain prepares for the German invasion. By the time she graduates, Franklin is determined to contribute to the war effort. Her father pressures her to carry on the family's charitable tradition. She replies that she would be of little use in anything but science. When he accuses her of making science her religion, she writes, In my view, all that is necessary for faith is the belief that by doing our best, we shall succeed in our aims, the improvement of mankind.
Cambridge really did for Rosalind everything that a good university should. It gave her a profession, a philosophy of life. It enabled her to distance herself from her parents. She emerged a mature, socially and politically aware individual, and she was ready to become a working scientist.
She joined the war effort doing research on coal. Her experiments led to a better gas mask, a valuable contribution to England under attack. She published 5 landmark papers, still cited today, and she was awarded her PhD. When the war was over, her experience earned her the job offer of her dreams, a research position in one of the best labs in Paris. One of her closest colleagues and friends at the laboratoire is Vittorio Lazatti, here in a restaurant that Rosalind enjoyed.
She loved Paris. She loved life in Paris. That was quite clear. She was very happy here.
She took a flat on a little street behind the Church of Saint-Sulpice in the 6th arrondissement. She wore the latest in Paris fashion, Dior's new look for the new woman. She shopped in the fresh air markets and took great pleasure cooking for her friends. She walked to work along the Seine, passing in the shadow of Notre Dame to the Laboratoire Central at 12 Quai Henri IV. It was here, in a collegial atmosphere, that Franklin perfected her techniques of X-ray diffraction.
She had just a feeling for the work, for experimental work. She loved it. She loved being in the laboratory. And a lot of people who were very, very good scientists, and even very good experimental scientists, view that as drudgery that they have to get through to get an answer, whereas she actually loved the process of science.
Franklin was gaining an international reputation, speaking at conferences and publishing in professional journals. An avid hiker, she took trips with colleagues to Norway, Wales, and the Alps. Her research was not without its risks. Lab workers were periodically checked for overexposure to X-rays, and when Franklin exceeded safe levels, she was upset that she had to stay away from the lab for a few weeks. After 4 years in Paris, she faced a decision. Should she stay in France or return home to England? She asked the advice of Dorothy Hodgkin, a renowned crystallographer and one of only 10 women to win a Nobel Prize.
And it was Dorothy's advice that it was time for her to make up her mind, and if she decided to have her scientific life in England, he should go back. And she left reluctantly. She was not very happy to leave Paris. I think that a decision she had to make, and it was to some extent a cruel one.
Franklin is offered a position at King's College in London, a highly prestigious research center. She is hired by J.T. Randall, the director of the biophysics labs, to create an X-ray diffraction unit to investigate the structure of proteins. She accepts the offer, but writes to a friend, "To change the banks of the Seine for a cellar on the Strand seems to me quite insane." But as she is leaving Paris, she receives a letter from Randall, shifting her focus from proteins to the little understood substance called DNA. Rosalind Franklin is 30 years old as she unwittingly enters an undeclared race to unravel the secret of life.
So this is DNA. It's really beautiful and amazing stuff.
It's responsible for heredity. It's the genetic material. Some would argue that it's the blueprint for every cell in your body. But at the time when Rosalind Franklin started working on DNA, it wasn't at all clear what DNA really looked like or how it might work.
In 1943, after a decade of work, Oswald Avery and his team at Rockefeller University transferred DNA from a disease-causing strain of bacteria into a harmless strain. The harmless strain turned virulent, strongly suggesting a link between DNA and heredity.
Avery's experiments showed that the genetic characteristics of one organism could be transferred to another. And he showed that DNA was the vehicle of that transformation, that DNA was the genetic material. But that conclusion was by no means universally accepted.
DNA was thought to consist of sugar and phosphates in long chains of some unknown shape. It also appeared to have just 4 other chemical ingredients called bases. But how could such a simple molecule be responsible for the diversity of all life on Earth? Some believed that discovering the structure of DNA would lead to an answer. That was Franklin's assignment when she arrives at King's College London in January 1951. Now a professor at King's, Raymond Gosling was a PhD student in biophysics at the time of Franklin's arrival.
When I first came in 49-50, what there was a bomb crater, remains of the Second World War. We had to walk round the bomb crater and in here to the main hall of the college. Now, our physics department was down that end of this corridor. Right at the end was a lab that Rosalind and I did the X-ray diffraction in. Yes, now this is quite close to what it was actually like. This is about the size of the room, and as you see, it's right in the basement. So that gives you a sort of taste to the bowels of the earth type environment in which the early work was done.
Despite the war-ravaged facilities, King's College was the place to be for DNA research.
Maurice Wilkins had his office just through these doors in those days.
Maurice Wilkins, a physicist fresh from the Manhattan Project, took some of the first X-ray diffraction images of DNA here. He had to improvise at every step to cope with the lab's antiquated technology.
Maurice came over and had a look at what I was doing, and we decided that, of course, this was a dreadful, leaky object. And he thought for a bit, then took a condom out of his pocket and said, "Here you are, my boy, poke the collimator through that." And so we did.
Franklin quickly adjusted to the physical limitations of the lab, but not to the segregated boys' club culture of King's College.
She was not happy in King's College. And all what she told us about it was almost incredible. I mean, the fact that they have a common room, a lunch place, which was forbidden to women. I mean, it sounded unheard. I mean, it was absurd to us. And it's not the kind of life we would like to have anywhere, to be forbidden a place because you are a dog or a woman or a Jew.
To make matters worse, there was confusion over who was in charge, Franklin or Maurice Wilkins. At the time of her arrival, Wilkins was on holiday. While he was gone, his PhD student Raymond Gosling was put under Franklin's supervision. When Wilkins returned, he walked into a vastly improved lab, but it wasn't his anymore. He lost his lab and his PhD student, and Rosalind Franklin, whom he thought was going to be his assistant, turned out to be better trained and already working independently. When he checked in on her progress, he was rebuffed.
She just said, go back to your microscopes, which bewildered me. What the hell's she on about? So we had a very stressful aspect which did not help joint work in our laboratory as a result.
The stressful relationship between Wilkins and Franklin arose from a miscommunication that originated with the director of the lab, J.T. Randall.
Well, here we have copies of Rosalind Franklin's working notebooks.
Sir Aaron Klug, Nobel Prize winner and former president of the Royal Society, was Franklin's last collaborator. After her death, he studied her notebooks and letters, including the one from Randall.
And in December 1950, he writes her a letter, and I quote, "This means that as far as the experimental X-ray effort is concerned, there will be at the moment only yourself and Gosling." That letter was not seen by Wilkins. And that fact, and the fact that Wilkins was not present when Franklin arrived at King's College in January 1951, led to a great deal of dissension later on.
She thought that she was an independent researcher, and Maurice thought that she was his assistant, right? And that was a misunderstanding. The responsibility of that misunderstanding lies in Randall's hands. Perhaps Maurice Wilkins could live that kind of ambiguous situation more easily than Rosalind would. She didn't like those kind of unclear situations.
The situation was inflamed by a basic personality clash. Franklin, articulate, passionate, and always up for a good debate, and Wilkins, soft-spoken, deliberate, and shy, just couldn't get along.
She was a pretty tough person, single-minded, spoke what she believed, and could in fact be quite fierce. And if she'd been a man, it would have gone totally unremarked.
Yet another barrier was social class, and a private life entirely separate from the lab.
She had a very full social life. I mean, I know for a fact that one stage I think she was going out with the first violin of the London Philharmonic. Now, that is a cut above the beer-drinking chaps like us who were sitting in Finch's. And so to that extent, she had her own flat. She wasn't living in digs. She didn't suffer fools gladly. She was very intelligent, and she desperately wanted to get on with this work. She was so convinced that it was there, like a ripe plum to be plucked from the tree.
Despite all the tensions of the lab, Franklin applied herself to the task with single-minded determination, setting her sights on solving the structure of DNA. But now, a new player was about to enter the game.
While Rosalind was setting up her new lab at King's College London, James Watson, much younger, 23 but with a PhD, had come to Europe because he wanted to study the gene, and he was convinced that the gene was the thing to study. This is going to be the secret of life.
Watson goes to a conference in Naples where Wilkins shows one of his early fuzzy diffraction images of DNA. Watson tries to meet Wilkins and wrangle an invitation to work at King's College.
I tried to talk to him, but Maurice, I figured, he's English and doesn't talk much to strangers. And so I left in sort of the vague feeling that it'd be nice if I could work with Maurice, but it wasn't a sort of obvious coming together of like minds.
Wilkins does not take the bait. But shortly after, Watson is invited to the Cavendish, a famous research lab at Cambridge University, headed by Nobel laureate Sir Lawrence Bragg. There, Watson is assigned an office with another physicist turned crystallographer, Francis Crick, an old friend of Wilkins. Crick and Watson immediately click. But an hour away at King's College, the negative atmosphere takes a new turn for the worse. Rosalind Franklin is given the sarcastic nickname that Watson will later popularize in the double helix, Rosie.
Oh yes, you know, it was with her walking around the lab, sort of swinging her bag, looking a bit like Thatcher on occasions, you know, she provoked this sort of thing. Some say, oh, we'll call her Rosie for a joke, silly joke.
A lot of people referred to her as Rosie behind her back, but nobody called her Rosie to her face.
Despite the hostile environment, within months of her arrival at King's, Franklin is producing amazing results.
Rosalind did the most professional work. She had a good camera, because she developed a good camera. She got superb pictures, the best in those days.
Within a few months, Franklin transformed the state of research at King's. But above all, she discovered that there were two forms of DNA.
Franklin's discovery that there are two forms of DNA is perhaps the most crucial step toward the ultimate discovery of its structure.
Before Rosalind Franklin discovered that there were two distinct forms of DNA, the A and the B forms, people were probably looking at mixtures of those two forms. It would be sort of like if you had a picture of Mickey Mouse superimposed on a picture of Donald Duck. It'd be almost impossible to understand what either Mickey Mouse or Donald Duck looked like.
The A is a drier, more crystalline form of DNA and produces more detailed images. The B is wetter, and how DNA occurs in living cells. It produces a simpler image, but reveals a key clue to solving the structure of DNA. The X shape in the middle is the diffraction signature of a helix. The significance is not lost on Franklin. She notes it in scientific shorthand and, according to Klug, presents her discovery.
In November 1951, Franklin gave a colloquium about her work and described the A and the B forms. She concentrated mostly on the A form, and the A form, she says, is likely to be helical, like the B. The B, there was unquestionably, in her view, was helical throughout. It was quite clear. But she was concentrating upon the A form because of the greater wealth of information you could get from it. That was her analytical approach.
In the audience that day is James Watson, sent by Crick to gather intelligence on Franklin's labors. Crick and Watson are planning to use a different approach to solving the structure of DNA: model building. Within a week, Watson and Crick invite the scientists from King's College to see their model.
So Rosalind just was terribly amused, and she never took prisoners anyway, so she was pretty sharp in her criticism of the model and explained in detail why it couldn't be correct, 1, 2, 3, and then we left.
The model of DNA touted by Watson and Crick is an embarrassing failure.
Well, Watson himself said very frankly he didn't really know enough crystallography to understand the meaning of their data. He missed that entirely, and he found himself really just preoccupied with her looks. Why was she so plain? Why didn't she wear lipstick? She might have been pretty if she'd taken off her glasses and done something interesting with her hair.
Lawrence Bragg, the head of the Cavendish lab, is humiliated and forbids Watson and Crick to continue their model making.
It was a happy moment for Rosalind and me because it justified her interpretation that you could build models, but you couldn't prove which was the right one. And here they were, the model builders, hard at it, and they'd produced completely the wrong model.
To Franklin, the incident is an affirmation of her training, that experimentation and patient analysis of the data will reveal the answer. But what Franklin may not know is that her unpublished findings will continue to make their way to Watson and Crick. And they are getting there through the deputy director of her own lab, Maurice Wilkins.
Gradually, Wilkins felt shut out of his own subject. So he began going up to Cambridge to talk to his old friend, and he was an old friend, Francis Crick, about DNA, which he was still interested in, and about this terrible Rosie, who was hoarding, he felt, her data. So inadvertently, Wilkins was the conduit. A lot of information from Rosalind and from King's actually passed its way to Cambridge, so that even if Watson and Crick were not officially working on DNA, they were speculating.
But while Crick and Watson speculate, Franklin continues to analyze and collect new information. In May 1952, she sets up the X-ray diffractometer to take an image of the wetter form of DNA, the B. Today, X-ray diffraction technology, vastly improved, is still used to explore molecular structure.
At the end of this glass capillary is a DNA fiber, similar to the kind that Rosalind Franklin worked with, and it is so small that it's difficult to see it with your naked eye. Rosalind Franklin had to bundle together 20 of these fibers in order to get X-ray diffraction images.
Now, scientists use DNA crystals, which give better results than these microscopic fibers. 20 of them bundled together are about the thickness of a human hair. And with X-ray beams at least 300 times stronger today than in Franklin's time, it can take only seconds to expose an image that took Franklin 100 hours. Now, a computer interprets the image and swiftly calculates a 3D model. But in Franklin's time, analyzing diffraction patterns could require thousands of calculations done by hand, and interpreting a single image could take more than a year.
So for Rosalind Franklin to go through the calculation, she had to have perseverance and motivation and a real drive and to do all of the calculations that was necessary by hand.
In May 1952, Franklin's perseverance and exacting techniques pay off, producing the sharpest image yet of the B form of DNA. She labels it Photo 51 and puts it aside while she continues her work on the A form. But around this time, Franklin will acquire another nickname, the Dark Lady. She is so unhappy at King's, she arranges to leave. She agrees to finish analyzing her data, write up her findings, and stay until the end of the year.
I was very sorry that she should find it necessary to leave, but of course appreciated that there was no alternative, that the Crown Prince and the Dark Lady were never going to get on together. He wasn't going to leave, so it was obvious that Rosalind was going to leave.
In the midst of this transition, someone gives Photo 51 to Wilkins.
I cannot remember how he came by this beautiful picture. It may have been given to him by Rosalind, or it may have been me.
Meanwhile, at the Cavendish, a new researcher moves into the lab with Watson and Crick. Peter Pauling, the son of the renowned guru of chemistry from Caltech, Linus Pauling. Only a year ago, Pauling had pioneered the same model-building technique adopted by Watson and Crick. With little experimental data, Pauling had come up with a structure for long stretches of proteins, a single-stranded helix. Now, Pauling sends his son a paper in which he proposes a structure for DNA.
Of course, we were upset. And the question was, could he be right? And we knew that Linus didn't have a good X-ray photograph. So could he have thought it through without any of the King's data?
The answer was no. Pauling makes some of the same mistakes that Watson and Crick had made on their first model. a 3-stranded helix with the bases on the outside. But Pauling's mistake will be discovered as soon as he publishes. Watson knows that if Pauling gets access to Rosalind Franklin's data, he could quickly come up with a correct model. Now, the race begins in earnest. Watson estimates he and Crick have 6 weeks to solve the problem. Around the time Franklin gives her last presentation at King's College, Jim Watson shows up in her office. He tries to show her Pauling's paper, perhaps to convince her that Pauling will beat them to solve the structure of DNA if she doesn't pool her data with him and Crick. And according to Watson's account, he implies that she is incompetent in interpreting X-ray pictures.
And as he tells us in the double helix, she began to advance toward me. And he said, fearing that in her hot anger she might strike me, I retreated, which is actually absurd. She was almost half his size.
Watson then reports that he runs into Maurice Wilkins. Wilkins shows Watson photo 51.
And when he saw this suddenly, well, I was surprised when I said, whoa, like this, you see. Thought, oh, well, must have been done the last couple of days or something. But it occurred to me it had been lying there for 7 months.
My mouth fell open and my pulse began to race, Watson says in the double helix. It is the clear X pattern, the signature of a helix, that ignites his excitement. But there's more.
From this photo alone, you can deduce the number of units per turn, per helical turn, there were in the helix.
The number of lines in the photo shows that each twist of the helix has 10 units, or molecular building blocks, and the dimensions of the image correspond to a helix of 34 angstroms per turn. Wilkins gives this crucial information to Watson.
So they get the basic parameters for building the helical backbones.
On the train back to Cambridge, Watson sketches photo 51 on his newspaper and reports to Crick. Based on Franklin's data, Crick and Watson go to Lawrence Bragg, the head of the Cavendish lab, and he gives them permission once again to build a model. They begin on February 4th, 1953.
Then they had another idea. They knew that data from all of King's biophysics unit, including Rosalind's work, was published in a report for the Medical Research Council.
In the MRC report, Franklin places DNA in a class of molecules with a certain type of symmetry, as these simple drawings in her notebook illustrate. The implications of that symmetry would be obvious to an expert like Francis Crick.
The MRC report contains Franklin's data, the symmetry of the A-form, all the crystal parameters, but above all the symmetry. It was this symmetry which told Crick there were 2 chains running in opposite direction.
2 strands each with the sugars and phosphates running in different directions, an anti-parallel double helix. But where do the bases go? On the outside, as Watson and Crick depicted in their first model, or the inside, as Franklin had told them? There were 2 important clues. A few years earlier, a British scientist, William Asbury, theorized that the 4 bases, adenine, thymine, guanine, and cytosine, would be stacked like pennies. And at Columbia University, Erwin Chargaff discovered that DNA always contains equal amounts of adenine and thymine, as well as equal amounts of guanine and cytosine. At first, Watson thought that the bases must be paired like with like, A with A, G with G, and so on. But an office mate, Jerry Donahue, shows him that he's using the wrong chemical forms. With the right forms, Watson then makes a giant leap. He finds he can fit the bases into the helix measured by Franklin if he pairs A with T and G with C. Arranged this way, the bases form the connecting rungs in a twisting ladder on the inside of a double helix. It is Rosalind Franklin's experimental framework, a collection of evidence painstakingly accumulated over 2 years, that guides Watson and Crick to solve the structure of DNA. And in another eureka moment, the structure rewards them with the immediate realization of how DNA replicates. Unzipping the helix produces 2 templates to create 2 new helices, each identical to the original. DNA isn't just a molecule, it's the blueprint for life. In one of the most famous understatements in science, Watson and Crick write, "It has not escaped our notice that the specific pairing we have postulated immediately suggests a possible copying mechanism for the genetic material." The day was Saturday, February 28, 1953.
That was the day that they went into the pub, the Eagle, and Crick told everybody, "We've discovered the secret of life."
Now that they have discovered the secret of life, they have another problem to solve. How are they going to prove it? Once again, they need Franklin. She travels to Cambridge to review the model.
And Watson writes in his book that her immediate acceptance of the model amazed me. But she understood immediately that the model was correct. What she perhaps didn't know is how much of her data they had known in order to build that model.
Rosalind's part in the great discovery was obscured by a series of maneuvers made behind her back. The thing is that Watson and Crick wanted to publish quickly to get ahead of Linus Pauling in California, but they were held back by the embarrassing fact that all the experimental work that had led to their great leaps of the imagination had been done at a rival institution at King's, and Rosalind's data hadn't been published.
According to Brenda Maddox, Bragg of the Cavendish and Randall of King's approached the editors of Nature to engineer a solution. They agreed to publish 3 articles within a single issue. Watson and Crick's article first, Wilkins and his collaborator next, and last is Franklin and Gosling's article. Its position at the end suggests Franklin's findings merely confirm Watson and Crick's model, instead of providing the essential data used to formulate it.
The Crick and Watson paper doesn't say in what particular respects they were indebted to Franklin for her work.
Sir John Maddox, later editor of Nature for 2 decades, shows how Franklin's contribution was obscured by Watson and Crick with a single guarded sentence.
They say, "We have been stimulated by a general knowledge of her work." But in fact, they had particular knowledge of her work. And I, as an editor, would have smelled a rat at that.
Franklin had written her own article a month before she saw the model. Inserted by hand into the original text is the sentence, "Thus our general ideas are consistent with the model proposed by Crick and Watson." Indeed, her ideas were consistent with their model because they largely based their model on her ideas.
What did Watson and Crick have without Rosalind Franklin's data? And the answer is almost nothing. They were poised to figure it out. Their work was brilliant, but they couldn't do it without Rosalind Franklin's data.
In fact, Rosalind Franklin could be said to be Watson and Crick's unknowing and unrecognized collaborator. By the time the articles appeared in Nature on April 25, 1953, Franklin had taken her new position at Birkbeck College in London. In her 5th-floor office under a leaky skylight, she often left an umbrella open on her desk to protect her papers. She headed the Virus Research Lab from 1953 to 1958 and thrived in Birkbeck's collegial atmosphere, much like her beloved laboratoire in Paris. Here, she made what she called her greatest discovery, working out the complex structure of a virus and locating its infectious element. She collaborated with Aaron Klug, who later wins a Nobel Prize.
She worked out the exact geometry, so it was important in history that you could actually do such things. The thing about Rosalind, she was single-minded, and she could tackle these large and difficult problems.
Franklin's virus work secured her international reputation and brought many invitations to speak in the United States. In 1956, she celebrated her 36th birthday while visiting universities in California and climbed Mount Whitney, one of the highest peaks in North America. But near the end of her trip, Franklin was suffering from severe abdominal pains. On her return to England, she was diagnosed with cancer. There is speculation that her work with X-rays may have triggered the disease.
She handled it marvelously.
Yeah. She was in the Marsden, the cancer hospital, and there she was in a private, well, a single room at the end of a corridor with work papers and calculations all around.
She was still optimistic and confident that things were going to get better.
Don Casper, an American colleague, recalls her struggle to climb from the basement lab to her fifth-floor office upstairs.
Up until the end, she was still working away. We had wished we could help her, but unfortunately, there was nothing could be done.
After a year and a half of terrible illness, painful treatment, she asked her doctor for a frank prognosis, and he told her to seek the consolations of religion. She was furious. She was not religious. She had a full agenda. She had an invitation to a fellowship in Caracas. She was too busy to die.
Rosalind and I were going to attend a meeting in Leeds, and she suggested that we could drive and go and visit some of the Norman cathedrals. When I arrived in London, I called her because I expected to stay with her, and there was no answer. And after several attempts to get her on the phone, I called Aaron Klug, whom I knew rather well, and he told me that she was in hospital. So until the very last day, she hoped that she could go to the countryside with a friend, right? And she died while we were at Leeds at the meeting.
Her epitaph reads, "Scientist. Her research and discoveries on viruses remain of lasting benefit to mankind." She died April 16, 1958. That same day, the London Times carried an article acclaiming her virus model, which was unveiled at the Brussels World Fair. Her obituary in the New York Times called her one of a select band of pioneers unraveling virus diseases and genetics. She went to the grave, never knowing how much Watson and Crick had relied on her work to make their great discovery. Or if she knew, she didn't care. In 1962, James Watson, Francis Crick, and Maurice Wilkins won the Nobel Prize for their discovery of the structure of DNA. Franklin's name receives no mention, save a passing reference by Wilkins. Her crucial contribution to their work becomes a footnote in scientific history.
Rosalind probably would have been forgotten, not by her friends. We would not have forgotten Rosalind. But, I mean, by the public in general, if we talk about Rosalind, it is because of the way Jim Watson offended her memory.
In 1968, James Watson published The Double Helix, his personal account of the discovery of the structure of DNA. In his book, Watson casts Franklin as uncooperative, unattractive, and incompetent in interpreting X-ray pictures. And yet Watson admits he needs her findings. He even boasts of using her work without her knowledge or permission, saying, "Rosie, of course, did not directly give us her data. For that matter, no one at King's realized they were in our hands." When the book was in rough draft, Harvard University Press asked those mentioned in the manuscript to read it. Many, including Crick and Wilkins, objected so strongly that in a highly unprecedented move, Harvard withdrew its offer to publish. The book came out with a popular press and became an instant bestseller.
But most of the main portraits were modified, all except Rosalind, who was dead, and every writer knows you can't label the dead.
Franklin's family and colleagues protested Watson's portrayal of, as one put it, that gifted girl who could not defend herself.
So Watson obliged, and he wrote a pious epilogue saying as a young man he had not appreciated the difficulties that women had in being accepted and making their way in science. And the epilogue is there, but it does nothing to alter, soften the character of this terrible Rosie.
Watson declined Nova's request for an interview. Franklin is now receiving some long overdue recognition, plaques where she lived and worked, and recently, Britain's Royal Society created the Rosalind Franklin Award to support women in science. When Sir Aaron Klug won his Nobel Prize, in part for the work he started with Franklin, he, unlike the DNA trio, honored her contribution.
As I said in my Nobel lecture, she made a profound impression on me, where she pointed the way to tackling important and difficult problems, no matter how long they took.
Rosalind died at 37, with no sense of having been edged out in a race that only Watson and Crick knew was a race. She died proud of her world reputation in coal and virus research. She was cheated of the only thing she really wanted, which was a chance to finish her work. In my view, her lost prize was life.
Those who admire Franklin take solace in her uncompromising dedication. For Rosalind Franklin, the joy of science was in the work itself and its ultimate reward, the betterment of humankind.
On NOVA's website, find out why Rosalind Franklin's Photo 51 holds so many clues to the structure of DNA at pbs.org or America Online keyword PBS. The Secret of Photo 51 video and the book Rosalind Franklin, The Dark Lady of DNA are available from WGBH Boston Video. To place an order, please call 1-800-255-9424. Nova is a production of WGBH Boston. Corporate funding for Nova is provided by Sprint and Microsoft. Additional funding is provided by the Park Foundation, dedicated to education and quality television. And by the Corporation for Public Broadcasting, and by contributions to your PBS station from viewers like you. Thank you.
I am PBS.